Chapter 2, Atoms and Elements. So, most of you are probably holding a pencil. Look at the end of that pencil. There's graphite there. Think about taking that graphite from the end of your pencil and cutting it in half, and then taking one of those pieces and cutting that in half, and just repeating that over and over and over again. Of course, you get to the point where it's too small and whatever you're using to cut it is going to be larger than what you're cutting. But if you were able, could you go on cutting that infinitely, or would you at some point get to a place where it could not be cut anymore? Just think about that. Eventually, what we would end up with would be individual carbon atoms. The word atom comes from the Greek word atomos, which means indivisible. You can't cut a carbon atom into smaller pieces and still have carbon. Now, atoms can be broken, they can be smashed, but not using a knife, not using any chemical processes. So atoms compose all ordinary matter. We mentioned this in chapter 1. If we want to understand matter, we need to understand the atoms that compose it. In 1827, Robert Brown was looking at water-suspended particles that had come from pollen grains. He was doing this using a microscope. And I've got a little video here that shows something like what he was looking at. Let's see if we can get this to play. See how those particles are wiggling? Perhaps not one of the more captivating YouTube videos you've ever seen, but illustrates a point. What made those little particles move? A kinetic energy. Yeah. So Robert Brown, looking at this, originally thought that perhaps the particles were alive, right? Because non-living things don't wiggle around like that, but living things do. But it was later realized that they're not alive, and what's actually causing those particles to move is they're being hit by water molecules. So we can't see the water molecules using a microscope like that, but we can see these very small dust particles from the pollen grains. And so this was evidence of atoms. So it's called Brownian motion. The source of motion is not the particles, but it's the water surrounding them. 1905, Albert Einstein developed a theory that explained Brownian motion. So it's the bombardment of the particles by the water molecules. So it is thermal kinetic energy. It's energy of those water molecules hitting the pollen and dust particles. So it's a little bit like a beach ball thrown into a crowd, right? And people hit at the beach ball, and you see this beach ball bouncing around. The beach ball is not causing the motion. It's the people underneath that are hitting it. So here we can see the beach ball, we can see the particle, we can't see the people hitting it, the water molecules hitting it. But this inferred the existence of atoms before they could be imaged with fancy electronic devices. So the work by Einstein and other scientists removed any doubts about the particulate nature of matter. This was a subject of debate for many, many years. Is it infinitely divisible, or are there smallest particles? So So fast forward to the 1980s, Binnig and Rohrer at IBM in Switzerland, their work led to the development of scanning tunneling microscopy, STM. The way this works is a very fine point is attached to a computer that moves this point back and forth across the surface that's being studied. This point is held at a fixed distance from the surface by monitoring the electric current that flows. So it's very close but not actually touching the surface. If the distance varies, the current that's flowing in that little gap would change. And so the computer adjusts it so that the current is always the same. So as you bring this tip across, and here's a higher layer of atoms, the computer recognizes, oh wait, we have to move this up. And so you can get a picture, a very indirect picture of the surface, and it gives an atom resolution. This technique can be used to image atoms and even move them. Now this is an STM image of atoms spelling out the Japanese kanji characters for atom. The blue are copper atoms, so this is a blue copper surface, and the red is individual iron atoms. So I got a couple of YouTube videos here to show you that illustrate how this works. If a picture is worth 1,000 words, how many words is a video worth? Come on. There we go.
So what we do to move atoms is a variation of what we do to see the atom in the first place. But we can't use light to see it, so we're not looking through a microscope like the conventional microscope we're used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on a surface and so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. If this is our atom on a surface, we can move the tip close and we start to form a chemical bond between the tip and the atom. And that chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. When we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
So using that technique, they made the world's smallest movie. There's another video that shows how they made the movie, and I'll put that on your playlist, but we're not going to actually watch it in class. So the resolution on screens is determined by how many pixels there are on the screen. And the smaller the pixels, the more pixels and the better resolution. So that's actually the ultimately small pixel. I mean, you can't get any smaller than a single atom for a pixel, right? So any questions or comments about that?
Assuming that costs a lot of money.
Yeah, if you just set out to do that, it would cost a lot of money. The reason they could do that is they are using the instruments that they already have to do their research. And so I'm sure it took a few guys a fair amount of time to do that, but it probably didn't set IBM itself back very much at all. But yeah, if you just wanted to start doing that from scratch, it would cost a lot of money. I don't think that's really a big deal in the future of filmmaking, but it's pretty cool. So just to help you get an idea of how small atoms are, the Library of Congress has about 35 million books. And if you add up the length of all the shelves, it's 840 miles of books on shelves. If you took all of the words in all of those books and wrote them using atoms so that they were the size of these characters, they'd fit in an area of 5 square millimeters. That's 1 millimeter by 5 millimeters. All the words in 35 million books. Atoms are really small. But they are the key to connecting the macroscopic and the microscopic world. Macroscopic meaning what we can see with our eyes, microscopic being things that are too small. So, an atom is the smallest identifiable unit of an element. There are about 91 different naturally occurring elements, and then there's a bunch more that have been made. Recently, the periodic table was updated, and these last few, like 118 and 117, those guys were given names. Those are all man-made. They're extremely unstable, and so you can make them, but then they just come apart almost immediately. So 91 naturally occurring elements.